Hi, this is a video tutorial on Lewis structure. So this is the table that you see in your discussion board, and what I will do is do several examples as well as these chemicals right here that I said I would do in the description. But before I do that, let me go ahead and do this example right here and this example right here, so you can see exactly how Lewis structures are completed. So this first example is H2NOH. This is, I believe, ammonium hydroxide. So in this particular chemical, I'd like to draw a table that shows the number of atoms. So in this particular case, I have 3 hydrogens. I have 1 nitrogen and 1 oxygen. Then I like to draw 2 columns. One column is called TVE, and TVE stands for total valence electrons, and the other column is OE, and that's called octet electrons. Now TVE is just the number of valence electrons each element contains. So if you look at the periodic table for hydrogen, you'll see that it's in the 1A column, indicating it has 1 electron in its valence shell, but there's 3 hydrogens. So that's a total of 3. For nitrogen, you'll see that it's in the 5A column. There's only 1 nitrogen, so that's a total of 5. And for the oxygen, you see that it's in the 6A column, and so it has a total valence electrons of 6. So the total number of valence electrons is going to be 5 plus 6 plus 3. So that happens to be, in this particular case, 14. Now, the octet electrons can only take on certain values. It's 2 if it's hydrogen, and it's 8 for every other element. So this is pretty easy to remember, because the number that you put here is either just 2 or 8. Now for hydrogen, I said that was 2, but there are 3 of them, so that's a total of 6. So each of these hydrogens right here can have, that's basically fulfilling its octet or its valence shell roles. Hydrogen first 2, since there's 3 of them, it's 6. Nitrogen, it's one of these O other elements, it's 8, and oxygen, that's 8 as well. So we have a total, I like to call this the fantasy column, because if all the elements had a full valence shell, then all the elements would be happy. So here what we have is 16 plus 6, that happens to be 22. Now it just so happens that if you take the octet electrons and subtract the total valence electrons, that's the number of electrons that will be involved in bonding. Now if you take the number of electrons in bonding and divide it by 2, because it takes 2 electrons to make a bond, that's the number of bonds. So what we have here is 22 minus 14, and that happens to be 8. And that's the number of electrons involved in bonding. If you take 8 and divide it by 2, what we have for this particular chemical is 4 bonds. So how do we draw the 4 bonds? You start by first drawing the central atom, and the central atom in this chemical formula is always either the first element in the formula, but it can never be hydrogen, or the second element. So this particular case has nitrogen in the center, hydrogens are flanking it, there's another oxygen followed by hydrogen. And what we have here is 4 bonds. So the way you do 4 bonds is you just draw lines between the atoms. That's 4 bonds. Now, how do we complete the octet? We complete the octet because we know that we use 8 electrons in the 4 bonds, but we need 14 valence electrons. That's how many electrons this particular chemical has. But we've already used 8. So 14 minus 8 happens to be 6. So what we have is lone pair electrons, and there are 6 of these electrons that are going to be lone pairs. So we put 2 here and 2 here. That's a total of 4. That means 2 remains, and that's where it goes. Now if you look, what you will see is that each of these elements in this structure has a full set of valence electrons. Hydrogen has 2 by virtue of the fact that it has a bond here. So the bond here actually represents 2 electrons. And you can represent it as a line like this, or 2 dots. And it's shared between this hydrogen and this nitrogen. So this hydrogen has 2 valence electrons, this hydrogen has 2 valence electrons, this hydrogen has 2 valence electrons. So all the hydrogens are satisfied. On the other hand, this oxygen has 8. There's 2 here, there's 2 here, 2 here, and 2 here, so that's a total of 8. And finally, what we have is this nitrogen has 8 as well. So what you see is that the Lewis structure is complete in this example. So let's do the next example. And the next example that I said was this chemical right here, SO3. SO3, -2. Now, this particular chemical is your sulfide ion. Remember, SO4, 2 minus is your sulfate. You should have learned that in chemical nomenclature. So this example has 1 sulfur and 3 oxygens. So let's go ahead and create a bond table again. This is my bond table right here. And I want to break it down to 1 sulfur, 3 oxygen. But now we have to pay attention to the -2 charge. So I'm just going to put that over here. I'm going to put my 2 columns here, but this time I'm going to put OE right here and TVE over here. Remember that OE column, octet electrons, can either be 8 or 2 if it's hydrogen. So if you have a sulfur, it's 8. If we have oxygen, it's 8 times 3, and that's 24. And this is not an element here, so we just leave that for now. Total valence electron, if you look up sulfur in the periodic table, you see that it's in the 6A family, so it has 6 valence electron. Above that is oxygen. It too has 6 valence electrons. 3 times 6 is 18. And now that's where this next line here is going to indicate that in this structure we have a -2, which means 2 extra electrons has to be added to this structure. So we'll just put it here. So we add the 2 columns. This happens to be 8 and 24, that's 32. 18 and 2, that's 20, plus 6, that's 26. The difference, octet electron minus total valence electron equals the number of electrons involved in bonding. So if we take 32 and 26, that's 6. And if we divide that by 2, that equals the number of bonds. So this particular structure has 3 bonds. So how do we draw this? Well, we do the first element is going to be your central atom, followed by flanking atoms. Now I can put the next oxygen up here, or I can put it down here. It doesn't really matter, but it flanks the central sulfur atom. Now I'm going to have 3 bonds. 1, 2, 3. Simple as that. Just draw a line. Now, how many remaining electrons do we have? Well, we know we need to have 26 in this structure right here, because that's the total valence electrons. There's basically 24 based on the sulfur and the oxygen, and then the -2 here indicates there's 2 more. So we have 26 total valence electrons, and we've used 6 in bonding. So that leaves a total of 20 remaining electrons, for a total of 10 lone pairs. So how do we complete the valence? Well, you see that this oxygen only has 2. It needs 6 more. Likewise, this oxygen has 2. It needs 6 more. Likewise, this oxygen has 2. It needs 6 more. Always complete the outer elements first and complete its octet, or complete its valency, and then you work with the central element if you have extra. So right now what we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 lone pairs. We need 2 more. The 2 more goes right there. And what you see in this particular example is that all the elements for this particular chemical has a complete octet. So this is how you do the Lewis structure for these chemicals that you have in this particular table. Now let me do the next one here. And in this particular example, I'm going to do O3. O3 is particular because there's only one type of atom, but there's 3 oxygens. Remember the 3 here? Whenever you have a subscript in a formula, it indicates that that element before it, there's that many. So we have 3 oxygens. When I do my bond table, by the way, there's a tutorial on my website on how to do Lewis structure. So if you need to brush up on this, look up my tutorial. In this particular case, I have 3 oxygens. I'm going to put OE here and TVE here. You know that oxygen is going to be 8 because that's the number octet electrons we'll always have. It's either 8 or 2 if it's hydrogen. So it's 3 times 8, and that happens to be, in this particular case, 24. The total valence electron is how many valence electrons oxygen actually contains. And it's in the 6A family, which means it has 6 valence electrons. So that's 3 times 6, and that's 18. Remember that the difference, octet electron minus total valence electron, that's the number of electrons in the bond. And if you divide that by 2, you have the number of bonds. So in this particular case, 24 minus 18, that happens to be 6. And if you divide by 2, you get 3 bonds. So let's go ahead and do this. One of the oxygen is going to be in the center in this particular case, and we put 3 bonds for this particular structure. Put one here, one here. Where do I put the third? You could put it over here. If you don't want to do that, you can put it here. But what you need is 3 lines representing 6 bonds. The 3 lines represent 6 electrons. Remember, you have a total of 18 total valence electrons minus 6. That's the number of electrons used in bonding. That 6 came over here. And you have now a total of 12 remaining electrons. So where do we put those remaining electrons? We put it on this oxygen here first and give it a complete set of 8. 2, 4, 6, 8. We put the other 4 here. So this too has 2, 4, 6, 8. Now remember that we've used a total of 2, 4, 6, 8, 10, or 5 lone pairs, but this represents 6 lone pairs, and we've already used 5. Where does the extra lone pair go? It has to go to the central atom. Now if you count, what you will see is that this oxygen has 8. There's 2 right here. There's 4, 6, 8. This oxygen has 8. There's 2, 4, 6, 8. And the central atom, oxygen, also has 8. 2, 4, 6, 8. So that would be the Lewis structure for this guy is ozone. You can do the same for SO2. For SO2, the structure is sulfur is in the center, oxygen flanks it. You can do the same for S3. For S3, you got sulfur in the center and sulfur flanks it. This guy also will have the very similar bond table as that. Why? Because sulfur and oxygen are in the same family, and so the total valence electrons are going to be identical. So that should give you a hint as to how to complete the other elements.